Okay, now for the correct proof. As usual, suppose all the things in the problem that x is a non-empty subset of n, and for contradiction we suppose that x has no epsilon minimal element. This time I define y to be the set of all things not in x such that they also do not intersect x, which in some sense is kind of saying that, or at least it gives me access when that time comes in the proof to think about the things immediately preceding any given element and then all things before it. But okay. I claim that this set Y is inductive. Trivially, the empty set is in Y. The hard part comes from showing that if A is in Y, then A plus 1 is in Y. Let's argue that A plus 1 must not be in X to begin with, and then we'll also show that A plus 1 has the other property necessary for being in Y. For contradiction, suppose that A plus 1 is in X. I claim in that case A plus 1 is in min in X. For contradiction, suppose that A plus 1 is in X. Consider any arbitrary element out of A plus 1, right? I'm trying to show that A plus 1 is in min, so I am going to take an arbitrary element out of A plus 1 and show that it cannot be in X. So, this arbitrary element of A plus 1, as usual, must either be in A or it must be equal to A. In the former case, I now get to use the fact that A does not intersect X, and therefore since T is in A, then T must not be in X. That made this half of the proof really easy. In the other half of the proof, since I assume that A is not in X, then under the assumption that T is equal to A, the result immediately follows. And there you have it. A plus 1 is in min in X, and so we know that if A is in Y, then A plus 1 is in Y. We only have half of the conditions, because now we have an extra condition for being in Y, so we need to show that A plus 1 does not intersect X. To do this, let's consider any arbitrary element of A plus 1 and show that it cannot be in X. Well, if any element is in A plus 1, then it is either in A or it is equal to A, and pretty much just as we saw a minute ago, both cases lead to this element B not being in X, and therefore their intersection is empty. From having these two properties, that A plus 1 is not in X and it does not intersect X, it therefore is in Y, this establishes that Y is inductive. Okay, now how am I going to use this to produce a contradiction as I have predicted I would be able to? Well, what I essentially have at this point is that X is some arbitrary subset of N, and N is a subset of Y because it is the smallest inductive set. I just showed that Y is inductive, and Y is in fact a subset of the complement of X and N. Well, in particular what I have in mind is that X is a subset of N and also a subset of its complement. The only set that can be like this is somewhat basic set theory, so I leave it without proof. The only set like this is the empty set. Therefore, we have shown that X is the empty set, but from the outset we have been assuming that X is non-empty. There you have it, contradiction.